There is one observation about the sea floor that has not been captured by the tectonic plate theory yet. This is a seamount chain. The plate tectonics has already explained mid-ocean ridges, deep ocean trenches, and right-angle fractures in the mid-ocean ridges. But the plate tectonics has not yet explained the observation of seamount chains. In other words, the plate boundary activities that we have just described do not account for seamount change, such as those of Hawaii, the Azores, the Canaries, Reunion, and Tahiti Island. None of these locations are at the plate boundaries. Tectonic plate theory uses a complementary theory, the hotspot theory, to explain seamount chains. Let's talk more about the hotspot theory. John Tuso Wilson postulated in 1963 that volcanic chains like the Hawaiian Islands result from the slow movement of a tectonic plate across a fixed hotspot deep beneath the surface of the planet. Let's repeat this. John Tuso Wilson postulated in 1963 that volcanic chains like the Hawaiian Islands result from the slow movement of a tectonic plate across a fixed hotspot deep beneath the surface of the planet. Hotspots are thought to be caused by a narrow stream of hot mantle, called a mantle plume, convecting up from the Earth's core mantle boundary. Mantle plumes are mushroom-shaped trails of hot rock that rise from deep inside the mantle, melt as they rise, and erupt from volcanoes at hotspots at the surface. The tectonic plate moves over a fixed hotspot, forming a chain of volcanoes. The volcanoes get younger from one end to the other. In this picture, you will see that a hotspot is a concentration of heat in the mantle capable of producing magma, which rises to Earth's surface. The Pacific plate moves over a hotspot, producing the Hawaiian Islands. Hotspot evidence supports that the plates move over the Earth's surface. Again, a volcanic hotspot is an area in the mantle from which heat rises as a thermal plume from deep in the Earth. High heat and lower pressure at the base of the lithosphere, or tectonic plate, facilitates melting of the rock. This melting, called magma, rises through cracks and erupts to form volcanoes. As the tectonic plate moves over the stationary hotspot, the volcanoes are rafted away and new ones form in their place. This results in chains of volcanoes, such as the Hawaiian Islands. According to Wilson's hotspot theory, the volcanoes of the Hawaiian chain should get progressively older and become more eroded the farther they travel beyond the hotspot. The oldest volcanic rocks on Kauai, the northwesternmost inhabited Hawaiian island, are about 5 million years old and are deeply eroded. By comparison, on the Big Island of Hawaii, southeasternmost in the chain and presumably still positioned over the hotspot, the oldest exposed rocks are less than 1 million years old, and new volcanic rock is continually being formed. Let me help you capture the notion of seamount chains with this analogy. Suppose that your shoe has mud. As you walk, the mud will continue to drop along your path. So think about the plate at the hotspot. At the hotspot, the plate captures magma. The plate spreads the magma as it moves. That is how the seamount chains are formed. Geologists have identified some 40 to 50 hotspots around the globe. Plate movement above hotspots is now considered an evidence of plate tectonic theory. The hotspots in the Central Pacific has created the linear chains of the Hawaiian Islands, thanks to the rapid movement of the Pacific plate, which is 9 centimeters per year. When plate movement is slow, at 1 or 2 centimeters per year, there are large gaps in islands and seamount chains, as in the Azores or the Canaries. In this picture, hotspots occur at locations on Earth's surface that have experienced active volcanism for a long period of time. So, we have more results of tectonic plate theory. We have explained the seamount chains by using the hotspots. Now we will talk more about the active volcanic map versus the plate map. We mentioned earlier that there are places in the world where earthquake and volcanic eruptions occur at the same place. There are places where there are only volcanoes and no earthquakes. Other places have earthquakes but no volcanoes. Our next task is to figure out how. Remember the issue of the occurrences of earthquakes and of volcanic eruptions. Also remember the issue of the correlations and non-correlations between earthquakes and of volcanic eruptions. The tectonic plate theory can also explain these occurrences, correlations, and non-correlations. This is our next task. In this example, you'll see that the first white arrows show that there are a few earthquakes in the center of the Pacific Ocean. The second arrow shows where there are a lot of earthquakes in the west coast of North and South Americas. The third arrow shows earthquakes, also defined as mid-ocean ridges going down the Atlantic Ocean. The final arrow shows a lot of earthquakes at ocean trenches around the Indian Ocean. Notice that the occurrences of earthquakes and volcanic eruptions almost define the plate boundaries. Notice also that the 3 types of earthquake faults can be connected to the 3 types of plate boundaries as follows. Transform plate boundaries are strike-slip faults. Convergent plate boundaries are thrust faults. Divergent plate boundaries are normal faults. Most earthquakes occur at plate boundaries. Divergent boundaries have normal faults. Transform boundaries have strike-slip faults. Convergent boundaries have thrust faults. The depth distribution can be shallow or several tens of kilometers deep in all boundaries, intermediate or up to 300 kilometers, deep or up to 660 kilometers. The 2 above occur at convergent boundaries, also known as the Wadati-Benioff zone. Let me repeat this. Most earthquakes occur at plate boundaries. Divergent boundaries have normal faults. Transform boundaries have strike-slip faults. Convergent boundaries have thrust faults. And the depths can be distributed as shallow or several tens of kilometers deep in all boundaries. intermediate, or up to 300 kilometers, deep, or up to 660 kilometers. The two above occur at convergent boundaries, also known as the Wadati-Benioff zone. Ridge earthquakes are relatively small and affect almost nobody because they take place 1 to 2 kilometers under the seafloor. Earthquakes in trenches are violent and very deadly. These earthquakes can be found in places such as Mexico, Guatemala, Chile, and Japan. Earthquakes are generally located at depths no deeper than the first 50 kilometers of the crust, except in trenches. The earthquakes in trenches can occur at depths of 300, 400, and 700 kilometers. Plate tectonic theory allows us to explain these observations as follows. In the regions in which plates are cold, rigid, and subducting, the potential earthquake locations could also be subducting in Earth's interior. There are also earthquakes along transform faults. They are very violent. Typical examples are San Francisco, California in 1906, the long fault of Antilles in Erzincan back in 1939, and the Jordan in Jericho back in 1250. In summary, earthquakes occur at places in boundaries where the plates rub each other, collide, or subduct in Earth's interior. Let me repeat that. Earthquakes occur at places in boundaries where the plates rub each other, collide, or subduct in Earth's interior. We'll continue talking about the active volcanic map versus the plate map by showing the following map. In this map, the first white arrows show where volcanic eruptions occur beneath the oceans. The second arrow shows some volcanoes, like earthquakes, are widespread along the west coasts of North and South Americas. The third arrow shows some volcanoes form in the middle of continents. The final arrow shows volcanoes occurring in the western edge of the Pacific Ocean. Again, notice that the occurrences of earthquakes and volcanic eruptions almost define the plate boundaries. Here in this example, a comparison of the map of active volcanoes and plate boundaries again show remarkable coincidences. Zones of oceanic trenches, or subductions, are also places where there are active volcanoes. Japan, Indonesia, the Philippines, New Guinea, Alaska, the western United States, Mexico, Ecuador, Peru, Chile, Italy, and Greece are places where such zones exist. Zones of oceanic ridges are also regions where there are active volcanoes. They are less spectacular because they are located 1 or 2 kilometers below the seafloor. Their effects rarely show up at the sea surface. However, the transformation faults do not produce volcanic eruptions. This is a major difference between earthquake distribution and active volcano distribution. Therefore, there is no correlation between earthquakes and volcanic eruptions here. Let me repeat this. Zones of oceanic regions are also regions where there are active volcanoes. They are less spectacular because they are located 1 or 2 kilometers below the seafloor. Their effects rarely show up at the sea surface. However, the transformation faults do not produce volcanic eruptions. This is a major difference between earthquake distribution and active volcano distribution. Therefore, there is no correlation between earthquakes and volcanic eruptions here. There are no active volcanoes in the former Yugoslavia, in northern Turkey, along the San Andreas Fault, or the Jordan River Delta. At these places, plates rub against each other. There is no vertical transfer of materials and no pop-up of materials from the interior of the Earth. Thus, no active volcanoes. Let's repeat this. There are no active volcanoes in the former Yugoslavia, in northern Turkey, along the San Andreas Fault, or the Jordan River Delta. At these places, plates rub against each other. There is no vertical transfer of materials and no pop-up of materials from the interior of the Earth. Thus, no active volcanoes. Besides the distribution of volcanism based on plate boundaries, we must add the volcanism of hotspots located inside the plates. Iceland, which was in the news in the spring and early summer of 2010, constitutes a unique case. We are dealing with a hotspot which is formed in the oceanic ridge and stayed. This is a kind of hybrid ridge hot point. We are dealing with a very complex case here. The 2010 volcanic eruptions in Iceland caused enormous disruption to air travel across Western and Northern Europe in April and May of 2010. From April 14th through the 20th, ash covered large areas of Northern Europe when the volcano erupted. About 20 countries closed their airspace to commercial jet traffic, and it affected about 10 million travelers. In this picture, Iceland is located right on top of a divergent boundary. In fact, the island exists because of this feature. As the North American and Eurasian plates were pulled apart, volcanic activity occurred along the cracks and fissures. With many eruptions over time, the island grew out of the sea. Let's view the earthquake eruption correlations on this table here. This is how plate tectonics explains these occurrences. We'll start with divergent boundaries, where oceanic-oceanic interactions, denoted here as OO, cause earthquakes and volcanoes, and therefore have correlations, which is indicated in the table by yes on the last row. Divergent boundaries, where continental-continental interactions, denoted here CC, cause both earthquakes and volcanoes, also have correlations, which is indicated in the table by yes on the last row. Convergent boundaries have oceanic-oceanic interactions, which cause earthquakes and volcanoes and are therefore correlated. Convergent boundaries have oceanic-continental interactions, denoted here OC, which cause earthquakes and volcanoes and are therefore correlated, which is indicated in the table by yes on the last row. Convergent boundaries have continental-continental interactions, which cause earthquakes, do not cause volcanoes, and therefore have no correlations, which is indicated in the table by no on the last row. Transform boundaries cause earthquakes, do not cause volcanoes, and therefore have no correlations, which is indicated in the table by no on the last row. Hotspots do not cause earthquakes. They do cause volcanoes and are not correlated, which is indicated in the table by no on the last row. The theory provides explanations for Earth's major surface processes, the geologic distribution of earthquakes, volcanoes, and mountains, and the distribution of ancient organisms and mineral deposits. Plate tectonic theory is a well-tested and widely accepted view. This theory best explains these observations. A theory becomes a paradigm because it can explain a large number of interrelated aspects. Tectonic plate theory does that. Therefore, plate tectonic theory is a paradigm. Here are 3 ways of measuring plate movements. Method number 1 includes the Global Positioning System, or GPS. The distance from a point on the Earth to a number of GPS satellites is measured. The difference in distances is used to triangulate the location of the point. Method number 2 includes determining the age of sediment that is immediately above any portion of the oceanic crust, dividing the distance from the spreading ridge by the age, giving average rate of movement relative to the ridge. Method number 3 includes determining the age of rocks and their distance from a hotspot, dividing the distance by the age. This gives the motion relative to the hotspot, possibly the absolute motion of the plane. Remember, there is a large selection of iMode education lectures which can further enhance your knowledge of earthquakes, volcanoes, climate, and energy. Thank you for your attention and good luck.